Welcome. So this question says, what is the magnitude of the force experienced by a positive 3 Coulomb point charge that is located 4 meters from a positive 12 Coulomb point charge? So let's draw it first of all. So let's start off with our 12 Coulomb charge here. And then we have our 3 Coulomb charge there. They're both positive. And the separation between them is going to be 4 meters. And just so we see what's going on, there's going to be a repulsive force. So we're going to have a force in this direction, an electrostatic force. And there's going to be a force in that direction, electrostatic force. And we can say, well, the electrostatic force is a vector. And we can say this is equal to Ke with Coulomb's constant, Q, and then Q over R squared. And then to make it back into a vector, we have a unit vector. So let's talk a little bit about this. What's going on in this bit here? Let's highlight this bit in the middle. What's going on in this bit in the middle is we're getting our magnitude. And you'll see it written in various forms. I could have Q1 and Q2. And in some regimes, they want you to include the signs, then we're going to mess with it. And other regimes, they don't. All I care about is the size of those charges. So I like to put a big and a little charge down. So I use big Q and little q very often. Sometimes I use Q1 and Q2. The R is the separation between the two charges, and it's squared because it's an inverse square law. Ke is a constant to make the math work out. If I'm working in newtons and I'm working in coulombs and I'm working in meters, then I need a constant proportionality. And that's my Coulomb's constant. And then this R hat is a unit vector which points in the direction of the force that I'm interested in. And so I look back at my diagram and I say, what is the force experienced by the 3 Coulomb positive charge? So I would be looking back here and I would say, well, there's the force experienced by the 3 Coulomb positive charge. I know its size, so then I would use a unit vector R hat to indicate its direction. And that's what that R hat is concerned with. If I was interested in the force experienced by the 12 Coulomb positive charge and I wanted the vector force, then my unit vector would be in that direction. Now, this question only asks, and the unit vector has a magnitude of 1. It's only a direction, it doesn't change the magnitude of anything. So if I want the magnitude of the force experienced by the 3 Coulomb point charge, then what I want to do is find the magnitude, and that's the bit that's in yellow. So basically, I say, well, then my force magnitude is equal to Ke, which is 9 times 10 to the 9, times 10 to the 9, that's the value of it, you look that up, times Q, and Q is equal to, the big Q is 12. And then little q was 3. And then R squared, R was 4, so that's going to be 4 squared. And this is just sums. It's going to be the force experienced by the 3 Coulomb charge is going to equal 9 second e to the 9. And then I'm going to multiply that by 12. And I'm going to multiply that by 3. And then I'm going to divide that by 16. And this would be 2.0 times 10 to the 10 newtons. And that seems like an extreme amount of newtons. Just a little side point here. Sometimes in tests I will say to you, you don't have to work out the constants. And so the answer in that case, what I mean by that is you don't have to multiply 9 times 10 to the 9 into this. So what you'd say is that would be 36 over 16 KE newtons, which would equal 36 divided by 16, which would equal 2.25 KE newtons. It's just a way of making the math a little bit easier. I'll be very clear, if you're in my class, I'll be very clear about which way I want the answer to be written. Now, this seems like a really big number, and that's because to some extent we're used to dealing with gravity. So let me just do an analogy. If this was a mass, say kilograms, and that was a mass in kilograms, then I'd say the force due to gravity was equal to big G, and then it would be big M, little m over r squared. And if I wanted the vector, I would put a unit vector on there. And the difference is, well, we don't, when we have 12 kilograms of stuff, we have very few charges in that 12 kilogram, very few unbalanced charges in that 12 kilograms of stuff. And G is a much smaller number than KE. If I look at this, G would equal, it's going to be 6.7 times 10 to the minus 11 is its numerical value. Well, I've got 9 times 10 to the 9 playing the same role as 6.7 times 10 to the minus 11. So just for the fun of it, if you like, if I want the magnitude of this guy, it would be 6.7 second e to the minus 11, enter, times, and let's say we had this in kilograms, so that would be 12 kilograms times 3 kilograms, and then divide it by 16. So I'm getting 1.5 times 10 to the minus 10 newtons. So if it was, so this is not the right answer, this is just for the fun of it. If we were talking about kilograms rather than coulombs, we would get a much smaller answer. You know, when you put a 12 kilogram mass next to a 3 kilogram mass, they're not pulled together noticeably because it's such a small gravitational force. But if I had 12 coulombs next to a 3 coulomb charge 4 meters away, it would be pulled together by a huge force. So there's a lot going on here. We'll get to the vectors later, but we'll talk about this for the moment. And then the final thing on this is, what is the magnitude of the force experienced by the 12 coulomb charge? And in a way, as a question writer, what I'm testing to see is if you have this sense of big things need big forces and small things need small forces. So that means that, well, you know, the force, this electrostatic force will be different from that electrostatic force. And Newton's third law still holds, you know, the force of A on B is the same as the force of B on A. So basically, it's going to be the same value. So Fe, let's designate this as the 12. Fe12 is equal to Fe, let's designate this as the 3, which equals 2.25 KE newtons, or if you like, 2.0 times 10 to the 10 newtons. Either one of those is a good answer. The point is, the force of the 12 Coulomb charge on the 3 Coulomb charge is the same as the force of the 3 Coulomb charge on the 12 Coulomb charge. And that's going right back to mechanics understanding. So there we have it.